Okay, Chaitanya sir, I hope we can start now. We can see a good number of participants in the class today.
Yes, sir. Yes,
Okay,
yes, sir.
okay.
So you can.
Thank you, sir. Thank you, Nagendra sir. So I hope Professor Prabhakar also will join soon. He already explained like he will be late. So let me give my introduction once again. I welcome you all for the today's session that basic introduction of computational fluid dynamics and myself Gangadhar Venkatramana, and we already met uh, directly in Vasu Engineering College during my last lecture on a short introduction course of fluid dynamics. And I'm a research scholar. Just once again, give small introduction that I'm a research scholar in the aerospace engineering of the Department of Aerospace Engineering, that IIT Kharagpur. So I heard that you are all from background of civil and mechanical with second year that who had already completed basics of fluid dynamics. So keeping in mind of your understanding that this course is just for giving you a small introduction of governing equations in fluid mechanics and their derivations, and then fundamentals of CFD using finite difference, and then we will later on see like how to use the CFD for our real life applications and engineering practical scenarios. So yeah, so we will see all these details in this course, and I request to kindly mute your audio. If you have any queries or doubts, you can unmute yourself. So let me go for the presentation today. So our today's topic is on, it's like a brief overview on the computational fluid dynamics. It will go for a few hours of lectures starting from today, and it will be on every Thursday and Saturday. The concept is the computational fluid dynamics, that uh, solving fluid flow problems using the computer is the basic idea of this computational fluid dynamics. We will go through the complete definitions of it. But before going to this idea of the topic that we go further, I just want to also give you a small recap of basics of fluid dynamics that we covered in the past class. So in the past class, uh, I showed you the setup, the experimental setup that we have and that we work experimentally for fluid flow problems. And I showed you what kind of problems we work, like we work on the fluid flow problems on external airfoils for the, which are like a bird wings or the aeroplane wings. We study those kind of forces acting on those wings due to the flow over it. So we measure, we quantitatively measure, or we qualitatively see the details of how this flow behavior on those kind of aeroplane wings or any aircraft wings or flapping birds or flapping or swimming fishes or whales, any kind of thing. And I also showed you the simple aim, like in the last class, was uh, understanding of streamline concepts, straight line and path line, which are the primary flow visualization components that one always interested to look at, so that the details of the flow can be visualized. And this is the experimental technique that I described last time. And this is the mathematical formulation of streamlines, straight lines, and path lines. And I also showed you how you can generate the streamlines in a computational way, or a mathematical model way. So these all things we described in the last class. So now we are moving on to the a course of computational fluid dynamics. Like it is again, I am instructing you that I'm starting this computational fluid dynamics by keeping in mind that you know all the basics of fluid dynamics, like the governing, not complete governing equations, like you can able to understand what is a Bernoulli equation, what is a continuity equation, and how a turbines work, and how dams forces on the dam or forces on the inclined plate, how manometer works. I just assume that you all are aware of these simple fluid dynamic concepts and boundary layer features, like some basic concepts of boundary layer. So assuming all these things that you are familiar with these basic fluid dynamics, I will also start the things that very from the basic level only, so that you can easily able to understand what is this computational fluid dynamics and how it is different from the basics fluid dynamics. So I already gave my introduction to you, and I would like to introduce my professor, which I did already in the last class. But for you, one more time, that my professor is Sunil Manohar Das, Dr. Sunil Manohar Das. He did his PhD from National University of Singapore and bachelor's from NIT Roorkela, and now he is an assistant professor at IIT Kharagpur in the Department of Aerospace Engineering. And he works mainly on the bio-inspired solutions like for unmanned aerial vehicles or underwater vehicles, and solver development for uh, fluid flow problems. So this is a simple uh, overview of his research. So without any delay, we can proceed to our today's topic, that is, what is a CFD? Sorry, kindly mute your audio and video. Okay. Okay. Our today's topic is like understanding what is a CFD. A CFD with the from our understanding of CAD, we know that it is computer aided drawing. The computer aided drawing. Before the computers, like it is usual practice that engineer uh, draft on a sheet with the standard formats of A4 or A3 with the using a drafter. I don't know whether these times in the engineering colleges are teaching the drawing on sheets. I think that you people did not try that how to draw. Whether you tried or not, I'm not sure. But drawing on a sheet is way different than drawing on a computer with, I mean, aiding with drawing with the help of a computer. In the same way, analyzing of fluids using, yes, any queries? If you have any queries, just unmute yourself and ask the query. 21%. Okay. So in the same way, the computer aided fluid dynamics, uh, it is not the actual definition of CFD. I will tell you why I frame this meaning of computer aided fluid dynamics. But I just want to relate this, what is computer aided fluid dynamics and what is a computer aided drawing, that people tried of drawing on the sheets and they are not able to draw more accurately as we are doing in the computers. So the name computer aided drawing and a big course on it and big research and very useful techniques that we are doing today, like even a complex 3D models, a very big geometries and assemblies, everything that you are already familiar with, that you can easily do in a SolidWorks software or a CATIA or a AutoCAD. Everything you can use it easily, and you are able to draw those things without like not using the conventional manner. In the same way, just relating for your understanding, but the actual thing is scenarios are very different that I'm explaining. In the similar way, the fluid dynamics, that what we are already studied in your basic fluid mechanics course or about the statics or about the dynamics, that you if you are using a computer for solving those kind of problems, that you can say it as a computational fluid dynamics. But still, solving all kind of problems does not solving all kind of fluid dynamics problem does not say it is a computational fluid dynamics thing, or you are not solving a problem using a computer. It's if you are using CFD as a computational fluid dynamics, that you are using a computer. Why we need a computer for the solving a fluid dynamics problem? Are we not able to solve by using the hand? So what actually, why we need a uh, computer for solving the problems? If you have a small problem like flow through a duct, this is your duct, and if you want to study the friction on the wall, how much of drag coefficient is acting because of the developed laminar. This is a developed region, like because of the boundary effects flow through internal pipe. If you have a flow through pipe like this and you have a boundary layer developing on the walls, you can see the friction effects in the wall and the loss of pressure. There is a pressure gradient. I hope you know this loss of pressure gradient equation. It's a very famous equation that one used to derive for loss of pressure gradient or the volume flow rate in fluid mechanics. If not, I suggest you just recollect that from your basic fluid mechanics course, how to calculate that pressure gradient or the volume flow rate through a pipe. So it is a one-dimensional problem that you can calculate by using the formulation that you learned in your basic fluid mechanics. But if my problem is like this, I am studying an aircraft and I want to understand the velocity uh, from velocity at every point in the fluid domain. Like this is my domain like I want to study. I want to find out the velocity on the entire aircraft or pressure distribution on the entire aircraft or the properties of fluid, like what is the density distribution around the entire aircraft that you are seeing in this image. If that is the case, what are the general properties? Like velocity. Let's take not more than 2 to 3 properties: velocity, pressure, and temperature. This is the first one I described. This is a very simple problem that you don't need any kind of computer or any kind of coding that you require. You can just easily do by means of the simple formulations that you already learned in the basic fluid mechanics. But if your problem is such a huge one, like if you want to scale up to thousands of meters or hundreds of feet, like the aeroplane flying at certain altitude, and that you want to understand how what is the pressure distribution and how this aeroplane is generating the lift, and how this jet engine is generating the thrust, how it is both, if it is generating the thrust in this direction and how the lift is generating in this direction, and what is the causing mechanism and how the flow or aerodynamics is helping here. These are all your brainstorming kind of things. It is not possible to understand by just doing the some hand calculation things. You need so much of, sorry, uh, okay, you need so much of understanding, like at every each and component, like what happening of the at the this jet engine. This is we call jet engine, or what happening the flow around this aircraft wing, and this is a wing, and this is a fuselage we call. This is called a fuselage, and this is elevator, horizontal tail also we can say, and this is rudder. Okay, so all these components combinedly, how it is helping to control this entire aircraft, and how it is deflecting and how it is taking a turns, maneuvers, everything. But it is all helping to create a force to move in particular direction because of the movement that you are generating the forces on the aerofoil, and that's how you're creating the lift. But what are the key components that doing this? How we can study? Are we able to measure these forces, or are we able to measure the pressure in real life scenario when aircraft is flying at that much altitude? It's not possible. So we can use the computer. With the help of computer, you can understand all these details. Okay. So what additional things that we can see in this uh, using the help of computer, not only for the flying aircraft, but also for a race car, where you need any engineer or the design engineers or the aerodynamics always used to try decrease the drag on these racing cars. By this time, I think you have participated in many racing car events, Formula kind of. I don't know the exact names of it, but you can heard of these kind of racing cars that you have many competitions that are going in the mechanical field. So the key components is not only to generate more mechanical power. If you are generating a mechanical power of 1,000 horsepower or something, and if you creating a very complex bluff bodies or complex obstacles to the flow, like the way that you see drag while driving a car, while driving a bus, if you are creating very complex obstacles to the flow, this 1,000 horsepower, in this 1,000 horsepower, maybe 20 to 30% will be used to overcome the drag itself because of your velocity. The flow has a resistance that stops your body all the time, so your energy always consumes here. So an efficient design is always necessary to efficiently use your energy that is generating by your engine, IC engine, whatever it is, so that you need to design in such a way the forces are very forces due to the air drag. Air always creates, if you are moving at such a velocity, air always creates a drag on the body. If you can reduce that drag, you can sell your race car, or you can move efficiently, use your horsepower. So that is also an aerodynamics generally do on a racing cars or an aircrafts. So where else you can also use this computer aided fluid dynamics. Make sure that the CFD definition is not a computer aided fluid dynamics. For your understanding, I'm telling it is a use of computer for dealing with the fluid dynamics. Okay, and then
Model.
some kind of aerodynamics also there people are doing on different kind of objects. It's not an useful thing to do, but people are interested on doing of CFD on many things that you can, if you are interested on fluid dynamics on CFD, you can see these kind of posts in social networks that are used to understand flow over different objects or different flow over animals. These are not a useful things that to do in the CFD. Why I mentioned this figure is CFD is not to just see all these kind of colorful images. Another thing also I can say CFD is a colorful fluid dynamics. Colorful fluid dynamics. It is not for seeing all these colorful pictures that you are seeing in front of your screen. It is to understand the physics from the uh, fluid dynamics point of view. You need to generate such a qualitative information or qualitative data such that one can understand what is happening and why these kind of forces are generating and what we can do for reducing those kind of forces. So, but it is not to generate a sim. I request you mute yourself. There's a lot of noise from your side, Mr. Kalyan. Is it someone else? Okay,
And the
thank you.
model.
So it is not about generating colorful pictures in the fluid flow. It is about understanding the things. Like if you are using any software that is a commercial software or any kind of open source software, you don't try to generate the pictures like this. You just try to understand the fluid dynamics. Then only you can say it is a computer aided fluid dynamics. Okay. Then what is the present scenario of generating the fluid dynamics that you can see if you find the memes or any kind of post in the social network for a CFD learners? People used to start directly with the CFD softwares like this. This is not intended, or this is not the correct way to start directly with the CFD software. You can start practicing and you can generate these kind of colorful images over in objects, like just for your hands-on experience with the tool. Like there are some commercial softwares like ANSYS Fluent and Star CCMD and many other commercial softwares for CFD. Like if you just click a button or if you just give some settings, it will automatically generate the properties or these kind of colorful images in the software. But unless you understand the mathematics, the basic fluid mechanics, the fundamentals of CFD, everything, not only this, all is many other steps also there. Unless you understand all these steps, you cannot understand what actually the CFD software is doing in the background, or you cannot predict what actually the physics that generated by this CFD software and why it is generating like that kind of solution. Okay. So I request everyone to practice more mathematics or more understanding of fluid mechanics and basic governing equations in the partial differential form or integral form, whatever it is. It is always suggesting that you keep on practicing the all the mathematics that you learn from your engineering levels or the plus two levels or the wherever it is. So what is the actual definition of a CFD? That in a general perspective, that what people thinks from other domains or the mechanical domain or whatever, if the user is new to the
Ask
CFD,
man.
the user, that is the user thinks in that perspective. But if you are a true learner of a CFD, that you needs to understand what is the basic definitions and what actually happening in the CFD. That is, that if you read that, let's read the definition of this. The physical aspects of any fluid flow are governed by the following three fundamental principles. We are only looking at the fluid flow. Fluid has many properties. It can be heat transfer there, it can be velocity distribution there, pressure distribution there, or it can be chemically reacting. So what are those background happening? What are the primary things that we need to understand every time? Whatever the flow situation it is, we need to understand whether the mass is conserved or not. Suppose if I have a pipe like here, if I have a pipe like here, and I have an inlet flow here, and I have my outlet flow here, and there is no point where your mass is escaping from the system. Mass is always conserved. Inlet mass is suppose 10 kg per meter square. If suppose you are taking some kind of element, and it cannot be a 9 kg or 8 kg. It should be exactly 10 kg per second. Whether your flow is rotation, rotation, whatever it is, mass should be always conserved. So that is what your mass conservation is. It cannot be decreased, or you know the fundamental principle: mass can neither be created nor be destroyed. Okay, so that principle you should apply. But if you are applying that principle in a very scientific manner, you can see the general equation that is not like simple A1 V1 equals to A2 V2. This is not the general equation of your mass
Ask
conservation.
man.
So you will get your mass conservation equation uh, when you consider your generation of equations by using proper systematic of mathematics. We will see that how to approach in a mathematical way of deriving this mass conservation for a system. In the same way, you will have Newton's second law of motion, like F is equals to ma. It is very important that you understand how the forces are also behaving inside your flow domain. If your flow domain is where suppose a bird is, consider a bird wing flapping. If you see a bird wing is flapping or something, uh, some wing is like this that is flapping by a bird, and you can understand these wings always flaps in the domain. That means these wings are generating the forces in the forces due to by exchanging the momentum with the surrounding air. If this is the surrounding air, the wings are flapping in the fluid, and these wings are generating forces by exchanging momentum with this fluid. So what is happening? How these forces are conserving? So again, you need to derive some kind of mathematical way, in a systematic mathematical way, that you need to generate another equation of motion that helps to conserve our forces in the domain. This is the second one. This is our first one, that is mass conservation, and the second one is the forces conservation or the momentum conservation, and the third one is energy conservation. Energy conservation means when you have a plate with a temperature of T equals to 1000 degrees and another plate with T equals to 0 degrees, it is equals to 0 degrees Celsius, you will have some certain kind of energy dissipating from, or transferring or conducting or diffusing, whatever it happens. If it is going from one media or another media, the amount of energy always conserved from one body to another body. If there is no other system from, or if there is a surroundings, the amount of energy transferred is always like delta Q is always conserved. It neither be lost or it neither be disappeared. So energy is also conserved within the body or within the system itself. Okay, so that is also the third conservation. That is also third important conservation that we need to look at. So all these things like mass conservation, momentum conservation, energy conservation, these fundamental principles should be expressed in terms of a mathematical equations, not a simple A1 V1 equals to A2. This is not a straightforward equation for a mass conservation. This is not a straightforward, but these are all our basic understanding of what is this mass conservation or what is this Newton's second law, the momentum conservation, or what is the energy conservation. Like energy conservation, we always can write del Q equals to del U plus del W. This is the heat transfer, and this is the internal energy change from your basic thermodynamics, if you see. And this is the amount of work done, right? Which is the most general form that we always need to see in terms of the partial differential equation of form. That is, we will see what is why we are seeing in partial differential form, why not we are interested in the algebraic form of the equation. These are all algebraic form. This is algebraic form, and this is F is equal to ma is also algebraic form, and this is also an algebraic form. But we are not interested in the algebraic form of governing equations. We are interested in the partial differential form of equations and how to derive those. Okay, that we will see in the next lectures. And then the computational fluid dynamics is the art of replacing these governing partial differential equations of the fluid flow with numbers. You see, we are replacing these partial differential equations. That those partial differential equations are not going to be solved in the form of algebraic way or not solving in terms of any symbolic format. We are directly replacing these partial differential equation with numbers. Suppose if you have uh, dx by dt, I can replace this dx by dt with some number like 20 minus 10 by 2. But is it correct? If I say in the computational manner, yes, it is correct. It will give you some solution with some accuracy. Okay. But if you are still wants to see the more accurate solution with this, what is dx by dt? I just want to see what is the dx minus the change in displacement like 20 minus 10 by 2. The same way that you are substituting in algebraic form. But here you need more accurate solution, like not simply directly substituting 20 minus 10. We will see 20 minus 10 by 2 plus 20 minus 10 by 2 whole square times 10 plus 20 minus 10 square by 2 whole cube times 10. There are more complex algebra is attached to this dx by dt that one needs to helpful to get accurate solution in the problem that we are solving. So that is what we are trying to see, like the governing partial equations are converting into the numbers. And then we are advancing these numbers in the space or time domain. We need the solutions, like whatever the solution of the flow problem. Suppose this bird is flapping its wing in the space. That means it is moving in the traveling in the space. Suppose this is the x direction, it is the traveling in the space in the x direction, and also it is moving in time, both x and time. So I want to know the forces generating by this bird at x equals to 0 meters, and at the same time t equals to 0 second. At the same time, I also want to know at what is the forces generating on by this bird at x equals to 1 meter, if it is traveled always 1 meter forward. At the same time, I also want to know it is the time, what is the time taking for traveling this 1 meter. This is all intercoupled. That means, if you're taking a system of 0 meters and 0 seconds as a starting condition of this bird, you can only say what is the force generating at this point. But you cannot say what is the time required for this bird by this the force generated on this, by using the force generated on this bird, and how much distance it is traveled. Like say if you say it is traveled 1 meter, you cannot say what is the time required for it. You cannot directly say it is 2 seconds, you cannot say directly say it is 3 seconds. This time or this distance are governing by your conservation principles, that is mass conservation, energy conservation, or the momentum conservation. Using these conservations, you are this bird traveling or this bird movement and the forces generation on this bird are intercoupled. All these things are intercoupled. Finally, those numerical description of the complete flow field of interest is our interest. Sorry, complete flow field is our interest. What is the complete physics that we seen already in the first image? This one. So finally, we want to see what is the complete picture of the flow field in the entire system. Okay, right. Then what is the else in the formal definition? I just want to delete this. So the same thing that we are describing here as the same thing I described that you all the fundamental equations in your fluid mechanics. You can see that dm equals to, this is a kind of this one. Let me take a pen. Okay. This is a kind of governing partial differential equation that your dm equals to rho ds dA. You may not be familiar with this equation. If it is familiar, that is well and good. And this is your Bernoulli equation in a differential format. This is also in differential format. This is well applicable for the one-dimensional kind of flow, for not three-dimensional solvings. And this is your famous continuity equation. And this is your famous, you can see Newton's second law. And this is the algebraic format of your Bernoulli's equation. So all these things are not derived by its own by the way of solution that you derived in your undergraduate course. The reason behind that all these equations are hidden in these conservation. This is the not a complete format, but this is the correct or actual format of mass conservation, that del dot v bar. Don't worry about the symbols. We will see all these symbols. What are these descripting? We will can practice in the upcoming lectures. This is what describing your mass conservation. Whether the amount of mass is really entering is the same is equals to leaving out of the system, whether it is same or not. This is a continuity equation. And the momentum equations, it is nothing but your simple F is equal to ma. If you see as a F is equals to ma, it is very simple. The force is equals to mass time acceleration by the Newton's second law of motion. But if you derive in a systematic mathematical manner, it see the equation becomes very complex and larger. And we generally call these equations as the Navier-Stokes equations. But it is only saying the same thing that you have already seen in the Newton's second law, F is equal to ma. The left-hand term is the force term. Sorry, this is the left-hand term is your mass and acceleration terms, and the right-hand terms are the force terms. But don't worry about all these terms. We will see the step by step what are actually each parameter and how these mathematically giving us insights of this mass conservation and the momentum conservation. So that is all the CFD. A brief picture. CFD is nothing but handling all these governing equations in a mathematical way and then converting into the numerics and then solving with a computer. So one more important definition is CFD that I started already in the beginning of the lecture. CFD is a computer fluid dynamics, computational fluid dynamics, or CFD is analysis of systems involving fluid flow, heat transfer. It involves, you must make sure that it involves always a fluid flow and the heat transfer. Heat transfer is not a necessary condition. That depends on whether your problem is there's an energy transfer is there or not. So heat transfer is not a necessary condition, but the necessary condition will be a fluid flow and associated phenomena like if there are any chemical reaction that chemicals are participating or not, or reactions are happening on those kind of things also it handles by means of a computer based simulations. So everything that you connected the things with a computer and solving all these fundamental and respecting all this, if I say not a solving, respecting all these fundamental governing things and using the computer, if you solve those problems, then it is called the computational fluid dynamics. There are various stages that involves in the computational fluid dynamics. Let's start this flowchart. Let's see this flowchart in from the right to the left direction. There is for using this computational fluid dynamics, any software, if you want to use, if you want to study flow over an object or flow through a pipe, anything, if you want to simulate, there are some commercially and available software. So like openly also available softwares are there. That is called OpenFOAM. So this is a commercial one. This is a open source one. You can, whatever the software that you are using, that primary requirements are you need to be able to model your computational domain. I will tell you what is that computational domain, but I will give you the terminology that involves in the CFD. I request you please note down all this terminology so that we will see one by one detailedly. Then we will see the geometry creation and then the mesh generation. Then we need to handle the governing equations, the suitable boundary conditions for those governing equations, and then we will see the results analysis. These results and analysis will come for the person who are very interested on the physics involved in the fluid mechanics more than the computer kind of person. If a computer kind of person, he can able to generate more the computational domain, the geometry, and the mesh generation. If one has an interest on one has both computational computer kind of person and one is interested on both the physics involved in the fluid dynamics, they can better handle this governing equation and boundary conditions, and they can couple this both uh, these above portion that I marked and the bottom portion, the resultant analysis and your computer processing. This is what we call the pre-processing. This first stage we call as a pre-processing that needs to be done everything with the computer that not linked with your any kind of physics, but with respecting the physics only, we generate these kind of computer requirements that is called pre-processing things. And once you are done with your pre-processing things, you need to understand your problem, and then we need to simplify it. We need to generate our governing equations
Mask man Ravali.
that is comes with a solver equation. Okay, solver executions and solver processing, and then you will see the post processing. So this is your final post processing of your results. All these things combinedly we call as a computational fluid dynamics. Okay, so these are the things that you can generate once you understand the computational fluid dynamics that you already seen in the first beginning of the lecture. And why do we need the CFD? We cannot count. We do these all these things with the basic help of analytical equations. The answer straightforward is no. Like it is not possible always
MOS.
to use. It is always not possible to use your
Mechanics
basic
of
equations,
solids.
not possible to use your analytical solutions or everything for understanding problems, very high complex problems. If you are involving the Tacoma Bridge kind of problem, like whether I don't know whether you've seen or not, a bridge with a cable kind of bridge that broken due to the completely because of high wind flow uh, in this direction. There is a bridge that in, we named as the Tacoma kind of bridge, and it was broken due to the high fluttering that occurred due to the free stream flow of u infinity, which is much greater than its flutter frequency velocity. That analysis also we cannot do by using the simple calculations, and then predicting of the tsunamis or the movements of the plates, oceanic plates, we can also simulate the oceanic flows kind of situations, which are highly complex in nature to predict. These kind of complex features, like one can predict the how tsunamis are appears if tsunamis exist or generated in the real life condition, and how it will damage the islands or the continents, and what are the effects for the prolonging time if a tsunami is generated for very far, and how it is affecting our very
Mask
far
man
regions.
Nagendra Ravali.
Those kind of things are also can be understand here. Okay,
Mask man.
so once you are able to generate these kind of understanding things, so you need a kind of system uh, that you can simulate these kind of flow features or in the oceanic plates or everything. One also important concept is this is a space vehicle, space traveling vehicle that everyone interested on it, because it is not possible to lift this much of load into the space, and one should travel at a speeds of very like 11 kilometers per second to 18 kilometers per second to travel up to escape from the atmosphere. If you are traveling at that much speed, the body what is used for this traveling vehicle will experience the temperatures of around 7,000 kelvin. Suppose if I am using a missile to blast a far distance continent or something, if you are that we are generally called as intercontinental ballistic missiles, that if you are doing within the atmosphere or it will go out of the atmosphere at the atmosphere also. So these kind of intercontinental ballistic missiles also travels at very high speeds that you cannot imaginable, those kind of speeds. So if the vehicle is traveling at that much speed, because of atmosphere interactions, it can generate temperatures of more than 7,000 kelvins. If that is the same that you're applying for a lunar mission, that is a something body is falling from outer space, or any space re-entry vehicles that can reach up to the 11,000 kelvins. These temperatures, if you are seeing a sun atmosphere temperature, the outer atmospherical temperature that we know around 6,000 degrees Celsius, and but these temperatures, if you see, it is more than that. So it is not even imaginable that to design how to resist these kind of temperatures. But what is the causing phenomena? Everything that you can study and the temperature and the heat transfer from the by using the computers and the computational fluid dynamics. Not only this space vehicle re-entry traveling, you can also find blood clotting and blood flow and flows inside your heart pumping. Everything about your brains, hearts, kidneys that flow inside a small veins that also you can simulate, and you can see by using the chemical deposition conservation equations also you can predict when is going to be because of the composites presence inside the blood, what will happen if somewhere you can find a clot in the blood, and after prolonged time what will happens to that position, or possibilities of brain strokes and heart strokes. Everything you can predict using simple fluid, not a simple, it's a complex kind of fluid dynamics, but you can make it the problem simple, and you can approximate the possibilities of solutions to this flow through veins in our body. This is very interesting kind of problems that the medicine and the fluid mechanics are coupled, and investigating these sciences in these days, you can find more number of research articles on in this area. So all these are the simple examples of computational fluid dynamics. There are very vast examples like predicting of lift and drag on the aircrafts of aircraft that are traveling in the atmosphere, hydrodynamics of the ships, power plants, combustions, and internal combustion engines. Also, you can simulate the turbo machinery if it is rotating at that high speed. The turbo machinery, you can know it rotates at very high speeds. Those kind of passages also you can simulate, and cooling of electronic circuits. If you are using high-speed gaming laptop, it is well known to you that it always needs cooling equipment, that a fans or a liquid cooling capacity, anything that you definitely need. So those kind of also simulates by can be simulated by using the CFD. For a chemical engineering, it is very much essential, and these are all typical examples that you can look over it. Then why this, even though that we are able to do all these things, why only the numerical still? Why not the analytical, like the basic mathematical model fluid dynamics that we already see? Why it is not sufficient? Why not experimental thing? Let's see the directly that its disadvantages and advantages. You can use the experimental thing that you can
Marksman.
that to understand everything. Like for experimental thing that you are able to capture more realistic things of kind of answers. But the problem is you need all those costlier equipments, or problem in uh, manufacturing those kind of equipments,
Good
and
Chaitanya.
measurement difficulties and probe errors and high operating costs. So all these things that you need to develop, and you need able to uh, set up these kind of things
MOSR. Good
which are
Chaitanya.
highly which are highly difficult to model in experimental scale, and it is not possible to operate with wide range of parameters in experimental way. But if you see the analytical ways, the restrictions are simple to the geometry and the physics, but you can only get and solutions for a linear kind of problems that are very simple kind of problems. But you want to find for hard kind of problems that you cannot use these analytical equations. It is not possible to generate the solutions also at some kind of steps. So that's why we are interested on numericals to develop the solution for very complex problems and for wide range of parametric sets that you want to investigate. But still, in these numericals also you have a problems like these kind of solutions like problems, truncation errors or round-off errors because of a numerics. There is a decimal errors always occurs that we generally call as truncation or round-off errors. And the boundary conditions also cannot be satisfied all the times. And the next thing is describing of your problem. How you are
Class ki
describing is
salo. Bye.
how you are describing your problem is also very important in this, like in this flow field. Like you need to able to understand whether your problem is internal flows, external flows, compressible flow, incompressible flow. Many things are there that one should understand what kind of flow I'm simulating, whether it is a laminar, turbulent, stationary, whether it is a body is stationary in my flow field or moving in my flow field, whether it is traveling with the sound speed or less than sound speed, what is the actual speed with respect to the sound traveling. If you compare, the sound is also playing very key role. So experimentalists generally do by using the flow, by visualizing the flow like shadow graph technique, shear and technique. These are all experimental techniques that you are seeing here. All these techniques helps us to understand or see the flow experimentally. That is we call shadow graph or shearing. These are for high speed flows, and this is for the low speed flows that you can visualize. And this is also a smoke flow visualization. This is highly turbulent kind of flow. Though you have an inlet here, it is a laminar kind of flow. You can see as a flow is highly turbulent. And then what are these governing equations? Once you decided what is the kind of type of flow that you are generating, your governing equations can be simplified for your understanding, for your further processing. Okay, suppose if you are dealing with incompressible flow or the flow has a constant density, these are all your governing equations that we already seen. That is the continuity equation, the momentum equations, and the energy equations. Okay, so in these equations, based upon your type of flow, you can simplify these equations. Like if it is the constant density, I can take out this term, and I can also take out, if it is a very implicit kind of problem, I can take out this complete terms. And if it is not an energy kind of transfer, I can completely take out all this energy equation. I don't need to worry about this. So I left with only these terms. So you need to state your conditions, like we just seen, what is the problem is, what kind of problem is, or what kind of flows. You need to justify all these things, whether it is this kind of problem or this kind of flow. Once you understand whether it is what kind, this kind of problem, you can simplify your complete full forms of Navier-Stokes equation or the continuity equation or the energy equations. And once you're done with your kind of equations, you need to able to classify what is the equation's nature, whether it is parabolic nature, hyperbolic nature, elliptical nature. Each nature of your partial differential equation have an identity in solving those or possibility in understanding its form of solution that you are getting in the numerics way. Once you are done with generating the solutions, you can again see we are done with governing equations and we are not done with the boundary conditions. But if you are able to couple this all these things, like we will see what are the computational domain, geometry creation, mesh generation in the upcoming courses. But we just see what are these governing equations in a just brief way. We will see more details of how to derive that and the boundary conditions and how to apply these boundary conditions, and the results and analysis also we will see by coding a simple problem, or analytical also we will see the solution of those problems and comparing with this actual CFD problem. This is a typical mesh of that we can generate. This is called a mesh, structured quadrilateral mesh. I don't want to confuse you by directly telling you about this mesh generation. We will see this detail of this, but this mesh generation that is required for generating your solution in the fluid domain. So what is this domain and everything we will see in the upcoming classes. But what is the main motto of this complete course is we will see the following contents. Some introduction to the vector calculus, very important for your fluid dynamics or your computational fluid dynamics, and some types of partial differential equations and how to apply the boundary conditions for it. And the discretization, that is nothing but a meshing. We call discretization, meshing, everything involves here. And how to integrate numerically with the generated things. And then we will see numerical methodologies for various governing equations of various parabolic, various differential equations and how to solve those. And the Reynolds transport theorem that we have been seeing that using these words like mass conservation equation, momentum conservation, and momentum conservation for implicit and viscous also we will separately deal. And then energy conservation equation. These things we will derive and we will see how it is playing or how it is handling in the flow field and what are the requirements for this. And then we will see Taylor series for the forward and the backward difference methods for handling this mass conservation, momentum, and energy conservation. How this Taylor series is able to help us for solving these partial differential equations. We will see some numerical methods for solving, additional numerical methods that are required for solving. And then using these numerical methods and the Taylor series formulation, we will solve the finite difference solution for a steady heat conduction through a fin. Fins are very common in the mechanical engineering for heat transfer kind of problems. Once you are done with all these things, we will go for CFD software ANSYS Fluent workshop for a 10 hours in which I will show you how to solve all these things by using the commercial kind of software. All these things that we can easily solve by creating the mesh computational domain in this ANSYS Fluent workshop. So this Fluent workshop can be only understandable by the person who can clearly able to see all these lectures and able to practice all these past lectures. Then only I can able to describe you what is happening in this ANSYS Fluent software in the background, and in the front end what are you are doing, and in the back end what is actually it is doing for you generating the results. So whoever very interested in understanding or learning this ANSYS Fluent workshop and the importance of commercial CFD package, it's a time to close jobs for the CATIA or SolidWorks, everything. It's not to close, but very advanced kind of things, or many people are already learning, or required number of labs are already available for the basic level of softwares for solid modeling and everything. It's a time for you to learn advanced things like coding in MATLAB, Python, AI kind of things, and fluid dynamics, like for a research kind of thing, ANSYS Fluent workshop. It is very basic and becoming very basic in engineering level or any normal practical level. Learning of your solid modeling is not sufficient for your job purposes or your future R&D or uh, higher studies purposes. You need always, your people always ask you for what are the higher level of languages you know. That is a kind of MATLAB or a Python higher level of languages. At the same time, what are the software skills additionally that you have? That is, if you say commercial kind of package, that is ANSYS Fluent. If you know these kind of tools, you will be in the top position for selecting any kind of required jobs, or for higher studies, for choosing in interviews, you can be easily grab the choice. So keeping in that motto, I'm going to teach this ANSYS Fluent workshop for a 10 hours class. We will schedule this, but it is only for the students, those who can clearly understand all these preliminary things that I stated above. And then only for the selected students, this ANSYS Fluent workshop will be conducted. So I request you all to participate enthusiastically and learn the things uh, and practice and clear your doubts in all these sessions. Every steps are important to understand this ANSYS Fluent software. Okay, and these are your some of the references that you can go through for your understanding of computational fluid dynamics. Um, Very important books for from the basic level to the advanced level. You can also verify. And thank you for your attention. With this, I would like to stop my today's lecture and welcome for your queries. Before going to the queries, I just want to request you all, please maintain your decency. It is not for the people who are not interested to this course. Who are very interested, they can join and they can listen and they interact. But if you're not interested, you can join and stay calm. Don't disturb the others who are interested listening this course. Okay, thank you. Now it's open for the session to queries.
Good evening, sir. Gangadhar, sir.
Good evening.
Gangadhar Venkatraman, sir.
Yes, sir. Prabhakar.
Sir, sorry, sir. I am not able to join at the start of the session. So,
no problem, sir. Thank you, sir.
So it's very informative, sir. So
Thank you,
actually, so from the next week onwards, so will you be able to provide the link, or shall we have to use the same link, sir?
This is the same link, sir. This is the same link that will continue for the all the classes.
Okay.
If it is necessary to change, we can change for the next classes.
Sure, sir. Sure, sir. No problem, sir.
Okay.
Sir,
So
actually,
this class, yes, sir.
Tell me, sir. No problem.
Yes. This class will be on every Thursday and Saturday from 7 to 8 p.m. So kindly take the notes of every steps that you are seeing here. It will be very useful if you take the notes and practice only. Unless you practice, you cannot get the details of it. Thank you. Yes, sir.
Sir, my doubt is actually, so once you complete the theory part, you will be starting the CFD software ANSYS software and all.
Yes, sir.
So,
Yes, sir.
so how the students will practice, because the software is not open source, it's commercially.
Yes, sir.
So
ANSYS Fluent is a
how the
commercial
students,
software. ANSYS Fluent is
so
a commercial software. Yes, sir. Yes.
how the students can access that software and practice. That is the
Yes.
uh,
Yes. I got your question, sir.
yes,
This
sir.
workshop we are going to convert in the offline mode, so I will come directly to the Vasu Engineering College and we will attend this seminar. But everyone needs a system. Uh, the ANSYS Fluent has a student version trial that everyone can install freely in the system that you have, or a laptop, or whatever the system provided by the institute. It
Okay,
has some limitations, so we will practice our fluid flow problems within the limitations of the free student versions. So everyone can register with their mail ID and they can download the free student version.
okay. For how many days it will be available, sir?
It is
Uh,
1 year, so it is valid for the
1 year.
lifetime, or 1 year it is valid. Yes.
Okay, okay, fine, sir. So before the completion of these sessions, we will have the offline classes, right, sir, for practice?
Yes,
No.
sir. Before the completion of this before the it is at the end of the session, like end of this complete coursework.
Okay, okay, fine, fine, sir. So after 24 sessions, we will be having the offline
No, sir. After 14 sessions.
14 sessions. Okay, fine,
After
sir.
14 sessions of theory classes, 10 more sessions on workshop of the ANSYS Fluent.
Okay, fine, sir.
Yes.
So in the campus itself for continuous 10 days.
Continuous 10 days.
Okay, fine, sir.
Only
Fine, sir.
for students who are able to pass the test on the CFD, or they
Yes.
must at least have the basic understanding of the content that I have been delivering here. They can only able to learn the CFD software. Unless they are unable to learn, it is not possible. Whether it is though learned, it is in offline mode. It is a waste of time to learning that without having the basics of it.
Yes, sir. Yes,
So
sir.
that's my keen request to everyone to decently learn this, uh, and having clearing your session queries, everything, and the CFD topic. Then we can go for the software handling of the software.
Okay, fine, sir. Fine, sir. So I request all the students, if you have any doubts, please raise your doubts so that our Gangadhar sir will okay, so answer your queries. Students, or else you can make use of the chat also. Is it okay, sir? Gangadhar sir?
Fine, sir.
Chat.
Chat is also working.
Fine.
I
Fine.
think some you're all registered with your Microsoft Teams. So if you're registered, people can, uh, I mean, whoever having the access of Microsoft, like DV Ravi Venkatakumar, I think he is access from his Microsoft Teams. So those kind of persons can chat directly.
Yes, sir.
Chat is also welcome. I can see good number of students, but I just want to see if you're all available here. Just please raise your hand who are really interested for your course on CFD and learning the ANSYS Fluent software, so that I can understand what is your true uh, intention or motivation of attending this lecture. Two, can I count more? Okay, 3, 5, 6, 7. Nice. Thank you all. So I believe you are all very interested in learning this course. So keep on practicing the things. Uh, Thank you so much for joining today. If you have any queries, we can discuss in the next week lecture. Okay,
Anyway,
so classes.
yes, sir. Anyway, we
Yes,
will
sir.
ask the students in the class and okay, sir. We will finalize the list, sir. The
Thank you, sir.
students list, those who are really interested to continue with the CFD course and all.
Thank you, sir.
Okay, sir.
Thank you so much.
Yeah. So thank you very much, sir, for okay, so giving useful information for all our students. And I
Thank
would
you,
like
sir.
to thank the coordinators of the program
Yes, sir.
session,
Chaitanya sir and
uh,
Nagendra sir. I also
Chaitanya
want to
sir,
thank you for you both.
Nagendra, yes, sir, Nagendra Prasad sir, and from the civil department we have Prem Garu. So thank you
Thank you,
very much,
Prince.
sir, for yes, sir, for your cooperation and support. Thank you very much, sir. So we'll conclude to this session, sir, in the next week. Thursday same time we'll meet again, sir.
Sure, sir.
Okay.
Thank you so much.
Okay, sir. Thank you very much, sir. Gangadhar, sir.
Thank
Good
you all
night, sir.
for joining. Thank you, sir. Thank you, brother.
Thank you very much, sir. Thank you, Chaitanya garu. Thank you, Nagendra Prasad garu. Thank you, Prem garu.